Good afternoon. I'm pleased to introduce to you Tony Uttley. Tony is the President and Chief Operating Officer of Quantinuum. So please welcome Tony.
Well, thank you so much for that. I appreciate it. And let me share. And then, so what is a quantum computer? There are some really incredible things about quantum mechanics and quantum physics that, when you put them together, allows you to take advantage of something that exists in nature. And in this particular case, it's three things. And I know I only highlight two of them here, but I'll talk about the third one as well. It's something called superposition, which is the concept that you can have something that we call a quantum bit, a qubit. And that qubit can not just be in a 0 state or a 1 state, but it can be in both of those two states at the exact same time. That is what a superposition is. And if you really want to blow your mind, it is, think of it like a sphere. And that sphere, if it was pointing true north or true south, that would be either a 1 or a 0, but it could be anywhere along that entire sphere. And it's probabilistically both a 1 and a 0 at the same time. So it's very powerful that it can have that entire value landscape between a 0 and a 1. The next really super cool property of quantum mechanics is something called entanglement, which is I can bring these two qubits together. I can perform an operation on them, and I will impart quantum information into both at the same time. And then when I separate them, they will retain that information about each other. And I can separate them in terms of distance. I can separate them in terms of time, and they will still retain that information. There's a correlation that exists between them. You might hear some people refer to it as they both are identical. That's not necessarily the case, but they will both retain information about each other. And that's really important when it comes to something like quantum computing. The third thing that we didn't put on here, that's also a critical piece of making quantum computers work, is that when you're doing a computation, the idea behind doing a quantum computation is that you're able to check out multiple answers all at the same time. And that's that power of having this superposition, is I can test out multiple answers at the same time. In fact, if I had something like 10 qubits, I could test out over 1,000 different answers at the same time. And if I had 50 qubits, I could test out 1.1 quadrillion values all at the same time. And this incredible third property is called interference. Now imagine that you could write a very elegant algorithm, a really elegant formula to put into the quantum computer. And the elegant nature of that formula was that all of the incorrect answers would interfere with each other as you're doing the computation, so that only the correct answer was left at the end. That's what a quantum computer can go do. So you have this ability to look at multiple different answers, basically all simultaneously. And if you are very elegant about the way you write your algorithm, you can come out with just the correct answer at the end. That's what makes a quantum computer so special. It's not that it runs faster than a classical computer. It's just that it runs very differently from a classical computer. And so let's talk a little bit about that. So in the traditional classical computer, including your laptop, your phone, you have this idea of bits, these transistors that are either a 0 or a 1. And in quantum computers, you have the same kind of idea, but they're qubits, quantum bits. But again, they could be a 0 or a 1 or anything in between. This idea that if you have a bit, it is either 0 or it's 1 all the time, means that when you have, as I said, that example of having 10 qubits, that could be 1,000 different values, or 50 qubits that could be 1.1 quadrillion values. If you had 50 bits, there's still only one value. If you had 10 bits, they're only one value. If you had 1 billion bits, it still only is one value, which is why that quantum computing, the expansion in computing power that you get from using a quantum computer is so big. Bits are done using electrical impulses. Qubits, there's actually varying technologies. So our company, Quantinuum, uses something called trapped ion, and I'll talk a little bit about how that works and why we can do what we can do. But there are actually multiple ways of being able to create these quantum bits today. And each of them has either some set of advantages and some set of disadvantages. And that's kind of part of the beauty of being in this industry, is that we aren't going to know how it plays out for years. And so being a leader now gives us a great opportunity, but it means that we're also racing other people who are obviously trying to be as good as they can as they develop their own quantum computers. So bits in classical computing, when you want to get a more powerful computer, you have to add more and more bits to it. But when you do, if you add, 10% more, you get 10% more computing power. That's not the same thing when it comes to quantum. Each quantum bit, each qubit, doubles the capability of the quantum computer. That's why when you have 10 qubits, you can have 1,000 values, but you keep on adding additional qubits up to 50, and now you have 1.1 quadrillion values. It's that exponential scaling that comes along with quantum computing that gives it one of its kind of superpowers. And then classical computers are really good at what they do. And what they do is they process a lot of information very quickly. Classical computers are good for trying to estimate something, trying to get close to something. What quantum computers have been proven mathematically able to go do that is superior is act like a quantum system. And there are other things that act like quantum systems. In particular, when you are developing a new molecule, it could be because you want a new material, or it could be because you want a new life-saving drug. How that molecule interacts with the world around it is really hard to simulate with classical computers. There's so many values, there's so many different variables that as you keep on expanding how complex this molecule is, you have to take more and more shortcuts. Whereas quantum computers act quantumly. And so you can actually create a very close approximation to how these molecules work in the real world. And so the promise of quantum computing is that as these quantum computers scale, you'll be able to not just help develop life-saving drugs faster, but you might actually be able to tailor those drugs to an individual person. That's the kind of capability that could eventually come with a quantum computer. So that kind of leads into why are different companies concerned about this? Why do they care? Why are different countries involved in this? This is one of the only technologies that has ever existed for which there are nationalized programs across multiple countries in the world, and they are to some extent competing. So you see big programs in the US, in the UK, in Germany, in Japan, in China, in Russia, in Canada. You see these playing out where it's not just tens of millions of dollars, it's billions of dollars that are being put in by these countries. And if you look at why would you care that much? Well, there was something that was at the heart of one of the, I won't say original, but one of the most important quantum proofs that happened in the last several decades, and it had to do with cryptography. It was something that's called Shor's algorithm. And what Dr. Peter Shor demonstrated was that you could get an exponential speed up in doing something called factoring large numbers. That doesn't sound very cool, except for that is how our encryption works today. So if you think about how, if you want to protect your banking information when you go into your do a transaction for your bank, or if you are a government and you're trying to protect your data, you do it by encrypting that data. And what has proven useful in encryption for a very long period of time is that it is super hard for classical computers to factor large numbers. And so you have these very large numbers that become part of the algorithm for how we protect data. Well, it turns out that quantum computers, when you get them large enough, have the ability to just untangle that encryption by being able to factor these very large numbers much more easily. And so that threat became a real and present threat to countries all over the world for being able to protect the data for their country and their country's national secrets, but also for keeping financial information protected and keeping people's patient data protected. And so we are transitioning into a world where we have to think about how we protect our data differently. And it turns out that the same tool that as it grows can become this threat, it also can become a tool for protecting our data. And so what you see on this slide are a number of different areas, not the least of which is this encryption within cybersecurity, where companies today are spending a lot of resources, and that means both people and money, to figure out how do we go and create the next set of products that help either protect our information or the next set of things to be able to discover new life-saving drugs, to be able to develop a new material for being able to sequester carbon, to try to reduce the impact of climate change on our planet. Same things with hydrogen storage. You see these really big, complex problems that face all of humankind that have the potential to be addressed with quantum computing. I'll point to another one on this page because most people don't realize, or should they, that over 1% of the entire world's energy supply, 1%, the entire world's energy supply is used for one thing, and that is to make fertilizer. There was a process, it's called the Haber-Bosch process. It's decades old. It's how we create ammonium nitrate to be able to go and use as a fertilizer for growing crops all around the world. And it is a massively energy intensive process. Yet we know, because plants can do it at room temperature, that there is a way to be able to do this same thing at room temperature, but we haven't been able to, as a species, figure out how it works. The promise here is that when you get a large enough quantum computer, you'll actually be able to simulate what plants are doing naturally so that you can create a new process that won't take this massive amount of the world's energy to go do. So, I mean, these are really just giant, again, humankind type of problems that the future of quantum computing has the potential to address. There is something that our quantum computer can do today that classical computers cannot. And the thing that it can do is actually create superpositions and actually entangle qubits. Now, why does that matter? Well, it matters because somebody, very brilliant somebody, came up with an algorithm and able to patent it, where if you are using our quantum computer, you can generate provable randomness. Now, why does provable randomness matter? Well, it turns out if you want to have an encryption key, and if you want to make sure that that encryption key can't be guessed by somebody else, then you need to have it be as basically perfectly random. The way the world creates encryption keys today is not perfectly random. It's something called deterministic, which means that it might be very hard to figure out how these keys are being generated, But let's say you were a nation state attacker, or you were a very sophisticated criminal enterprise. You could just be very patient and collect a lot of data over enough time. And with that data, you could start to figure out what is the next key in this sequence. Our quantum computer, even today, without getting any bigger, is able to provably generate what we call near perfect. And I can't say perfect because everybody who's a cryptographer would throw up all over this, but we can do something that is so asymptotically close to perfect that it is the best encryption keys that both can ever be generated and have ever been generated. And we can do that with our quantum computers today. So one of our first products that we've actually launched into the market is called Quantum Origin, and it is a service for generating these encryption keys.